Okay, so the first thing that we want to talk about in this chapter is about the computer systems. So first of all, a computer program, it's set up instruction. What does that mean? So if I go to we're going to look at this a little more detail as we go forward. So if I go to my CPU in my computer, the CPU, all it does is going to execute instructions, and it only understands zeros and ones. So whatever we write is going to be translated to zeros and ones, and it's going to have instructions. So right now we're working with computers, 64-bit machines. That means each instruction is going to be 64 bits or 8 byte. 1 bit is a 0 or 1. 1 byte is 8 bits. So that's the instruction goes to CPU. CPU looks at this instruction and says, based on the first few zeros and ones, it knows what to do with it. You will learn more about this in your assembly or architecture class if you are electrical engineer or you are computer science. You're going to take that assembly class and you're going to learn about these things over there. I'm not going to spend too much time on it, just kind of an overview. How does it look like? So you would remember some of these things for your first test, and after that, you can do whatever you want to do with it. All right. So we are talking about the softwares, basically putting a bunch of the programs together to do something. We talk about editors, translators, system management. So in general, what we do with the editors is going to help us, it's going to help us to enter our code. So it's going to highlight some stuff for us. It's going to tell us if something is wrong. It's going to help us to bring something in the program. So it's just kind of a help for us to type in our program. But just typing it in there is not going to do everything. We need to take that code and change it to zeros and ones for the computer to understand. Computer language is only zeros and ones. So if I want to talk to somebody who doesn't understand my language and I don't understand that person's language, we need the translators. So I say something, that person translator is going to take my words, change it to the language the other person can understand, and vice versa. So that would be our translator compilers that we're talking about. And of course, system managers program are the one that's going to take care of the behind the scenes stuff. That's why we can see things, we can share things, we can do things. So that's the bottom line with these things. So for the hardware, we have different types of hardware. We have so for the hardware, we have PCs, that's called personal computers, generally used by one person and doing the daily work. And PCs these days are doing a lot more than what we need. And they just have a lot more power, a lot more memory than we need. And then the next one would be called workstation, is a lot more powerful than the PCs. Generally, they would have more CPUs, they would have more power of processing, they have more room of storage, they have a way of storing stuff so we can recover it. So they may have 5 hard drive and would write things to them in a way that if one of the hard drive fails, you can just replace it and everything will be okay. So we don't lose stuff. How do we keep track of things so we don't lose it? Having a lot more, and we can have more people on the workstation. So we can have a remote connection to the workstation. I'm working on my workstation and I'm not even aware that some other people are in my computer and using my CPU to do some other work. So that's the power of workstation. And of course, the last one, which is the mainframe, we talk about the clouds and all those kind of things, is a lot more powerful computers. They can handle a lot of users at a time. So they would have lots of users depending on the mainframe on it at the same time. They have a lot more storage. They might not have it on it, but they can handle multiple storage. So a lot more things to do. And of course, you're going to definitely need support staff to take care of daily stuff, backing up stuff, doing things. So definitely it's going to be utilizing the multi-users. Networks and the computer organization, this is something that we want to talk about. So we have input devices. The input devices is going to bring the data to our computer. So a standard input device is the keyboard. So when we want to put some kind of a data to the computer, we're going to use the keyboard to enter. Later on, we learned some other media of bringing data to our computer or program that we are working with. And then the next one would be the output devices. So the reason that we're bringing this data, we want to do something with it and bring out the output. The standard output right now is the monitors. So when we finish up with our project, we're going to display it on the monitor. And of course, we have our processors, which are doing the processing for our program. So just like manufacturing, we get the raw data coming in, we process them, and we're going to have a finished product. So here, the input device is going to bring the data to our program. Processor is going to be doing the processing that needs to be done based on the instructions that we put in our program, and it's going to give us some kind of a display at the end to see the result. Main memory is a fast storage area, of course, because it's the fastest one. It is very expensive. It's going to sit next to the CPU, and CPU is going to pick up the information it needs, instructions from the main CPU, from the main memory. So CPU doesn't look at anything else except the memory. Basically what it says, if you want me to do something, it has to be right here in the main memory. Main memory is generally much smaller because it's very expensive than my program. So my whole program doesn't fit in main memory. We're just going to bring part of my main program. And of course, if it needs any data, the data is going to come with my instructions. So my code is going to be translated to instructions, and my data is going to come with it. And when we're executing the program, if it needs the data, it's going to pick up the data and it's going to produce something else. Secondary memory basically is any other storage than main memory. Your hard drive, I don't know if you're still using a DVD, CDs, the network drives, USB, anything that you save your data or whatever you have. Main memory generally doesn't stay. So when you turn off your program, your main memory is going to go away, but your secondary storage are going to stay there. So when we are talking about the data, remember the instructions always the same size. So if you have a 64-bit machine, that means it's going to use eight bytes to store the instruction. But the data doesn't mean it's going to be the same size. So the way that we're going to address the memory, it is just basically going from the first one, second one, third one. That's the numbering for it. So if you think about the old-fashioned addressing, you would say, come to this alley and go to the fifth house to the left. So I had to count 1, 2, 3, 4, 5 to get to your house. So that's the way the memory is addressed. So it's basically you start with 0. We'll talk about that later. You don't have to worry about it. And then it's going to know the number. So if I'm looking at this one, is the byte number 9. The next one is byte number 10. That's the address. Now, computer only understand zeros or 1. So it's going to be either 0 or 1 that understands. That's all it understands. That's the only language it understands. So anything that goes to the CPU has to be in zeros and ones. They were writing the programs with zeros and ones early on in the programming. It was very, very hard to do. And then pretty soon they find out that just one bit is not going to be enough to organize the stuff. So they came up with 8 bits. That is going to be 1 byte. So 1 byte is 8 bits. So the memory is just going to be organized with bytes. So when we say, the addressing of the memory, it just goes 1 byte to 1 second byte and so on and so on. So that's going to be the address. If we have the data that's going to be longer than 1 byte, it has to take more space. So languages like C++, like Java, what they do is they ask how much of data do we need, room for the data, by identifying the data type. We go over that in chapter 2. So if I need more space, so for example, in this one, I need 3 bytes, then it's going to take 3 bytes for it. Then it's going to take 2 bytes or 1 byte, depending on the data that I want to store in there, then it's going to use that. You already seen int, that's integer, is numbers without the decimal. So if I have numbers that doesn't have a decimal point, I don't need room in the memory for decimal point portion of it. I'm just going to use as much as I need for my integer. So we will see this kind of a data going to the computer. So it's 1 byte. They are just exactly like each other. So C++ likes number. So it does keep track of numbers. So when it sees this one, it's going to automatically change it to 65. Sorry about that. So if I want to make this as a character, if I want to put this in a character, then it becomes a character. So if I push capital A, that one is going to go to the computer, and vice versa. If that's coming out of the computer, it's going to display capital A for me, or if it's a number, it's going to show me 65. Now, if this is going to be as part of the instruction goes to the CPU, it's going to look at the first few bits, and it's going to decide what is it supposed to do with this. And then based on the rest of this, it's going to figure out what to do. That's going to be part of your assembly class. I don't want to spend too much time on that one here. But if you're interested, we can talk offline and we can go over those things. So some basic stuff, overview of these things, and it's going to show up in your test. So be sure that you understand these things. If you have any questions, then let's talk about it. All right, so in here, your program is going to come to the memory. And when your program comes to the memory, it's going to have 2 sections. Actually, it's going to have 3 sections, but we're going to talk about 2 sections here. The instruction, that's the code that we write. That's going to be translated to zeros and ones. And then you have your data, where you keep the thing. So in your last program that you did, you had 3 data in there. One was number of pods, P's per pod, and the total. So you had 3 variables. So it's going to check the data type of that. Based on that data type, it's going to put them right after each other in the data section. And with the size and all those things, we're going to talk about it in next chapter. So it's going to go, the data goes here, and the instructions will go here. And the languages like C++ are very efficient. They know ahead of time how much room do they need in the memory. That way, they don't take more than what they need. The secondary one is going to be something outside of the main memory that we're going to keep our permanent storage. I don't know why the floppy disk is here. That was a long time ago. Believe it or not, we had something really floppy, and I put a lot of work in one of my classes in there, and my neighbor kid came to my apartment and took that one out of my box and kind of, you could bend it. And all my was political science. I was like 12 chapters of reporting, and then she just bent it and all of them went away. So it was actually called, it was floppy, so you could bend it. Anyway, I don't know why it's over here, but those are the secondary storage one. When we are accessing memory or any kind of a access, we call a random access memory. That means I can go directly to that address. So I give you my home address, you can directly come to my address. Sequential is I'm going to give you sequentially where I am. So instead of you coming directly to my home, you have to count where I am. I'm going to tell you fifth house from the left. So you come in, you go 1, 2, 3, 4, 5. Sequentially, you're going to get to where I am. That was generally the tape. It is still used for storage. So if I want to find something in a tape, I have to rewind it, start from the beginning and look for it. I cannot jump into the area that I need. But random access memory, I can jump into any address that I want, and I don't have to start from the beginning. So we have a central processing unit. The main CPU is going to be CU. It's going to be executing instruction. So it's called fetch and execute instruction. So it's going to bring the instruction, operating system is going to do that, from the memory next to the CPU. It's going to check it to be sure it's good. And if it's good, CPU is going to execute that. And of course, if I want to create any kind of a virus, I try to do it in that instruction. So when it comes to the CPU doesn't know what to do with the instruction. That's where we're going to have a crash on the program. And if I am able to do that for the operating system, then my whole computer is not going to work. So next to the CPU, there is a little CPU, mini CPU, is called ALU, Arithmetic Logic Unit. ALU job is just doing mathematics. That's all it does. So when CPU sees any kind of a mathematic calculation, send this to ALU. ALU job is just to do math. And the funny thing about it, it only knows addition. It doesn't know anything else. So it does addition, subtraction, multiplication, division, all those kind of things to addition. It's very, very interesting how it does that. So if it wants to do subtraction, it takes the number, it makes it negative number, and then add it to the other one. If you want to do the multiplication, it just add, shift. So it's using shifting, and it's going to add it to create multiplication and division. But that's all the ALU is going to do. I'm sorry, I'm going too fast on this one. It's just I am kind of short on time today. But this is going to be available for you if you want to look at it again. So the operating system is the software. Remember, every time I want to execute the software, it has to be memory next to CPU. Otherwise, CPU is going to refuse to look at it. So everything has to be in the main memory, including the operating system. Operating system is the one that's going to be running everything in the background. So if I need my data to move from hard drive to memory, that's the job of operating system. Now, the problem is going to come in that my operating system is a software, and a software has to sit next to CPU. Otherwise, CPU is not going to look at it. So if this is my memory, the top portion is going to be the required operating system portion, and the bottom portion is going to be my scratch part for my operating system. Of course, in real life, this is upside down, but I don't want to confuse you guys any more than what we can. So what happens is when I have my computer running, the required part of my operating system is going to be sitting over here. So when you go and want to buy a software or you want to do something, it's going to say minimum requirement of the memory. So it's going to be the base part of it is going to be sitting over here. Remember, memory does not have room to keep all the software, including the operating system. Operating system is huge, so it's not going to fit in the memory. It's going to have a minimum part that it needs. It's going to go here, which is going to be running the whole time that your computer is running. And then it's going to have a scratch part over here. That's for the things that it needs at this time, and then it's going to dispose it later. The way that we dispose things in the computer system, we don't have an eraser to go out there and erase stuff. What's going to happen is it's going to mark the block of that area that's available so we can write on top of it. So that's why FBI goes to people's houses, they took their computer, they can restore the loss, the files that's deleted, because there is no eraser in there. You just go in there and says, this block is ready. And if you don't write on top of it, the data still is there, it's available. So you turn on your computer, there is nothing in here, CPU doesn't see anything, nothing is going to happen. So there is going to be a very small operated area, the very small area that is powered by battery, and it's going to keep some stuff in there, and that's going to be for our date and time of the computer, the first instruction of my operating system, and things like that that I need. And it's going to stay there. And when I turn on the computer, the first instruction is going to go here. The CPU is going to pick up the first instruction and it's going to start executing. So the first job of the operating system is what? To bring its own stuff and put it right here, the minimum requirement. So that's the time it takes when I turn on a computer, and you can see that in the older computer. It takes a little bit time before it shows me anything. It has to bring the required code in this section, and then it's going to do its own checking, and then it's going to be ready when everything is ready over here in this portion of the memory. And then while it's running, if it needs something, let's say I want copy and paste type of thing, so it's going to bring it here, it's going to use it, and when it's done with it, it doesn't need it anymore. So that would be the scratch part of the operating system. So we have different operating system. Unix environment, very solid, was created for multi-user from way beginning. And then the DOS came along, the Microsoft copied Unix and made it for the PCs. And then Linux did the same thing. It took the Unix and made it for the PCs. And then Windows came from DOS and made it more window type. And Macintosh came after that. Nowadays, the architecture of Macs are exactly the same as PC. So they don't have a different architecture. They used to have a different one before 10. So that's for that one. And then we move on to, so we have our program that's going to be, later on we think about it. So we have our program, we have our data. So you saw that in Tuesday. You're running a program, it needs some data. It's asking you for 2 numbers. So you put those 2 numbers with the program that you have, and then it's going to create an output, which is the result of multiplying for these 2 numbers. That's what we did already. So because zeros and ones was very hard to program, then they came up with the symbolic way of doing it. So that would be the assembly language. And then we have higher level languages. These are the languages that's more like an English type. So C++ is in there too. And the high level languages, we're going to need something as compiler because we're writing it more of an English type things. And So we need some kind of a compiler to translate those things to zeros and ones. So before the high-level languages, we had assembly language that had symbols. So add X, Y, and Z. You would add X to Y and put it in the Z. You will practice on this in assembly class. And so it's close to the machine language. So I have to tell everything manually. And that would be a work to do. So in here, if I want to add two numbers together, I have to load the first number, this X in here. I'm going to put it in my register 1, and I'm going to load my Y in register 2. I'm going to add register 1 to register 2. I'm going to put the register. We have different types of assembly language, and most of them don't put the last one for the add. So I am going to store register 0 to Z. So these variables are sitting in memory. So I'm going to go, this is the way we were doing the assembly, and that's why I don't like it. You do all of these things instead of a plus sign that we use in our high-level program. So we're going to say, go to the memory, bring the X content, and put it in the register, which is next to the CPU. Then go get the other one from the memory, bring it and put it in this register. And we would add these two registers together and put the result into another register. And we're going to take the content of the register, put it back in the memory. So all of these things happen when I just do a class in my high-level language. That's why we like high-level languages instead of doing the assembly. But in case we have to learn it, we have to learn it. So that's what we have for this. I'm gonna have the recording for this available later on today, so you can go back and check some of these things if I'm going too fast. So the job of the compiler. So we are writing high-level language programs. What we're gonna do is, first thing first, compiler is gonna check my syntax. So every language has its own syntax. In real life languages, we're talking about grammar. So if I want to write anything in any specific language, I have to follow the grammar for that language. So we're going to check the grammar first. So it's going to check the syntax, and it's going to complain about the things that doesn't like it. So if it's, in our case, you see that every statement of C++ ends with a semicolon. So if it doesn't see that semicolon, it's going to complain about it. It's going to try its best to find exactly where it is, but sometimes it has to go around it. So if it says it's missing semicolon, I have to go to the location. Maybe it's before it, maybe it's after it. It's in that area. Sometimes it cannot tell you exactly where it's supposed to be. And it might give you, so if it gives error, that means it cannot compile it till you fix it. It may give you warning. Warning means I see something is wrong, but it's not a showstopper. You can move on, but maybe you want to fix this. So something that may come up that, let's say you have an integer and a character that mixed up, and then it sees that it can potentially be a problem, but we can move on. So that would be a warning that you can compile it with warning, but you cannot compile it with error. So it goes through that. My syntax is okay. Then it's going to compile it. It's going to take my code and it's going to create zeros and ones for it. It's going to create the instructions based on the code that I have written. And it's going to tell how much room do we need for our data area. So now when we have our C++ program, we're going to compile it. And then when it's compiled, it's going to give us a machine language program when we're going to be running machine language program. Okay, so when you compile your program, if you go to the directory, you're going to see these files over there. We don't care for it that much, but it's in zeros and ones, so you might not even be able to see it correctly. Then we're going to be running this machine language program, and we're going to add the data to it, and then we're going to get the output. So some parts can be potentially compiled before my program. So if I need some modules that's already done before, I can bring them to my program. We talk more about this later. Some of these parts can be already compiled. So if it's already compiled and I already created the object code, I don't have to compile it again. I just bring so I have two ways. One is to bring the code, add it to my program and compile everything together, or compile the other one already. So when I add it to my compile code, then we can move forward. So in here, I'm compiling my program. I'm bringing those extra code that's already compiled. So they are in the binary and my code is in binary. They put them together as a linker, and then we're going to have the complete program. That way I don't have to write it again. I'm not going to go through that. So this is going to be the conclusion of this one. We're going to have an activity on this, activity 1.2, to answer these questions.